In this video, we will look at linear models and residuals for those models. For example, the sales for a company in billions of dollars in certain years is given in the table below. So in the years 2002, 2004, 2006, 2008, and 2010, we know the actual sales for the company in billions of dollars. And you can see in this graph that the sales are plotted as points versus the years after 2000. So these data points represent the information in this table. In order to make predictions, however, it would be good to have an actual model for this data. So the linear equation y equals 0.2x plus 0.7 is one possible model for sales in billions of dollars each year, where x is the number of years after 2000. So this is one possible model for the data in the table, and you can see that this line is not perfect. So the blue line on this graph is the linear equation y equals 0.2x plus 0.7, but some of the data points are above the line and some are below the line. So one important question to ask is, well, how good is this model? It's possible that there would be a different linear model that's better. So to determine how good this model is, there are a few different things we could look at. And the first is called the sum of the residuals. So the sum of the residuals tells us how far away the data points that we have are away from the line. You can see that some are above and some are below the line on the graph. So let's calculate what this linear equation would give us in each year. And I'm going to add that to our table. So that would be y, or the predicted sales using this model. So this model predicts that in 2002, we would have 1.1 billion in sales. In 2004, we would have 1.5 billion. And this is just plugging in x equals 4 for x in this equation. And continuing, the y value for x equals 6 would be 1.9. The y value for x equals 8 would be 2.3. And for x equals 10 would be 2.7. So these values in blue are the predicted sales values based on this linear equation. So now to find the sum of residuals, we determine how far away are these predicted values, these y values, from the actual sales in the table. You can do this from a table or you can do it from the graph. So from the table, the actual sales in 2002 were 0.1 above the predicted sales. In 2004, the actual sales were 0.2 below the predicted sales. In 2006, the actual sales were 0.1 below the predicted sales. In 2008, the actual sales were 0.3 above the predicted sales. And then in 2010, the actual sales were 0.2 below the predicted sales. So the sum of residuals is just taking each of these values, so plus 0.1 from 2002, minus 0.2 from 2004, minus 0.1 from 2006, plus 0.3 from 2008, and minus 0.2 from 2010, and adding all of those values together. So the sum of residuals for this linear model is negative 0.1, just adding all of those separate residuals together. So an actual better predictor of how good this linear model is called the sum of squares of the residuals for this model. And with the sum of squares, we're going to take the same residuals from just the sum of the residuals and we square each one and then add them together. So that would be 0.1 squared plus 0.2 plus negative 0.2 squared plus negative 0.1 squared plus 0.3 squared plus negative 0.2 squared. One thing that the sum of squares does is it makes all these values positive. So this is squaring each of these individual residuals. And then we add all of those values together. So this would be 0.05, 0.15, 0.19 is the sum of squares for this model. It's actually easier to compare different models using the sum of squares residual. Because really we won't see how good this model is until we compare it with a different linear model and see if that sum of squares and sum of residuals is lower. So our goal is for the sum of squares residual to be as low as it can be. That tells us that our model is good or that the data points are not far away from the line.